Hello, everybody. Yes, scroll down a little bit. Yes, please. Before we start this session, I would like just to make an announcement. And for the session tomorrow in the morning, 9 o'clock, I would like just to make sure that you know that there is a farming. Well, let me point it. Up here. There are two sessions and separate sessions, and they are at two different rooms. So please take note. Okay? Thank you. And now we can put up the presentation.
Are you guys going to sit on the panel?
Yes. Well, yeah. Well, I think we can sit afterwards for questions.
Okay.
Yeah. The before last, down. Yes. Okay. So welcome to the session on Earth observation, exposure, and feature extraction. My name is Daniele Erlich, and I'm coming from the Joint Research Center of the European Commission. So I would like just to introduce this session by telling you that we will have three speakers. And I will just introduce the session and give you an overview, because I feel I should report to you some of the issues discussed in the forum, in the online forum. I think they deserve attention, so I will provide that. And the three presentations are From Space to Ground, Current Trends and Capabilities of Remote Sensing, delivered by Mark Lucas, Exposure Database Development at Different Accuracy Level by Inder Claire, and then state-of-the-art information techniques delivered by Guido Lemoine for the GRC. So we would like the important is that we will have 15 minutes presentation and each panelist, and then we will have the questions saved at the end. Since we are also online, I think the questions may come in via Twitter, and then they will be written down and will be read to you. So if I feel, though, that since we have a relatively small audience, the question of this room can be asked directly over the microphone, okay? So we'll have a timekeeper, and I think we are almost ready to start. Yes. So actually, I will provide an overview. Okay. So I would like just to dwell on this slide that you have seen before, just to tell you why are we using Earth observation. So it is really to map exposure. This is the topic of this presentation here. Now, exposure is, in this case, it's the building stock. We see the 3D building. But I wanted also to say that the reasons why we are doing it is really because, oops, hold on. It's because we want also to, maybe I should have a microphone. Can you hear me? Yeah. So it's also because with satellite imagery, you can get 3D information. For example, you can get also landscape information that are extremely useful for hazard modeling, for example. So with 3D, you're not only getting the building height, you can get also the 3D. There's some timing on. I will not dwell on this. This is the second presenter, Mark Lucas, will tell you all about satellite imagery and future trends. So for us, physical exposure, for us coming from the remote sensing community, is really about the building stock. So the building stock, the important thing we have heard also in the Capra session this morning is about where the buildings are, how big they are, the sizes of the buildings. And of course, you need to tell something also about the vulnerability of these buildings. So I feel that the remote sensing is good for identifying the buildings, locating them, measuring the size. Not so good for qualifying the buildings. For that, I think you can do something with the remote sensing, but it's probably other technologies can be of use. And then eventually, somebody has to give the final decision of what the building is all about, and probably this is a civil engineer. I just wanted to tell you also about this global settlement maps, because they have come into this forum discussion. There have been, there's a lot of discussion about also within GEM that will be taking place tomorrow about global settlement exposure. And I think the global settlement map is a good proxy. So we'll tell you about global and regional a little bit. And then the more detailed urban land use map and building stock maps will be more covered by the third presenter in the clear. So let me just tell you a little bit about this global built-up map. I think some of you, especially if you're coming from the remote sensing community, are familiar with the night lights that have been used also to produce the global rural-urban map of the world. But I think there's one new product, which is the MODIS at 500 meters, which has been just released maybe 1 month ago. And I think that product deserves attention. That will be interesting to understand from you if that product could be considered for other global settlement map. Here we show just an example over one island, which is in the Caribbean, Guadeloupe, where on the top left we have the reference map made of building footprints. Just to say that MODIS could be used to at least to identify the very high concentration of built-up in the world. I will tell you also, there has been discussion about the continental urban land cover. I think we have been exposed to Africa cover, for example, the Korean land cover in Europe. There are urban land cover for the North America. I have learned recently there is one also for India, so it's very good. And the fact for the remote sensing specialists is always very difficult to understand how this map should be derived, because in this case, for example, you have in pink the built-up, and you can see there is a continuous gradient of built-up density, and then that has to be mapped in categories. Where to draw the line is the big question. And it's an important question if you have to produce a product over large areas, continents, and those maps have to be comparable. Then it becomes an important issue. So what we have learned is there is no really automatic method that allows you to do that over the entire globe. Otherwise, probably we would have it already, since Landsat is available globally. So, as I say, it's also not easy to define the legend and to define a class within a legend. And for that reason, it will be also difficult to validate. But if available, probably it should be considered also for as a proxy for exposure, if available. Good. So I think what we are so happy now in the last 10 years is that we have the very high resolution satellite imagery that are really incredible, have changed the way we are doing remote sensing, because we really can see every single building, and out of that you can make, for example, an urban land use map, like the one I'm showing here. This is Nairobi. It is, I think, the disaster risk community, I think, is familiar with this. What the remote sensing community would like to understand is really how to define those classes, and is there a legend or a classification scheme for urban areas that could be used. That would be interesting for us to understand. So the imagery, as you see from this, can tell you very much about the city. You can see the very dense area, in this case, is as an informal settlement in Kibera, in Nairobi. At the same time, you see different patterns. And those patterns, these urban patterns, you can tell very much from the very high resolution imagery. If you go at the coarser resolution, and this is an spot imagery, probably you can still see very well certain patterns, but other patterns are much more blurred. And again, the question comes again, where do you draw the line if you make a land use map? And this is an raster image over the same area. So these are some of the questions that we, remote sensing community, have been addressing. But we would like to get guidance also from the disaster risk community on what urban classes to define. In terms of what imagery to use, we have probably a simple rule. Some of us have a simple rule. If you are able to identify and draw the footprints of the building, probably you can do lots. You can derive lots of products. If you are on the upper scale, coarser resolution, then probably you can derive only certain type of products, probably more urban land cover, and in that case you suffer from what I just mentioned before, it's difficult to define what a given class is. In the online discussion, we have also discussed the different feature extraction techniques. For example, what I'm showing here is object-oriented. It has been started to be used, especially with the very high resolution imaging. Object-oriented is the semi-automatic that allows you still to draw, to segment the image quite efficiently, but still you have to be there and then decide where every segment of the imagery has to go. But it has been used extensively by a number of researchers that have reported in the forum to map urban patterns within cities. In this case, it's informal settlements in cities. And this was kindly provided by ITC colleague. So built-up mapping. But as I say, if you have the very high resolution satellite imagery, then you can do so much. And I would like to introduce also the automatic detection of built-up areas in this case. So what I'm trying to say is that you can get every single building, but that is quite time-consuming and it has a cost attached to it. But you can also do it automatically. The product is simpler, but it's simpler, but it can be generated automatically. So you can go over large parts of the world in an automatic way. Of course, the accuracy still has to be properly taken into account. But I want just to show an example. This is again Nairobi, and we have the built-up map is a simple built-up binary map. Built-up is black in this case, and the city. As seen, the city that mapped in this way, it looks like this. And in my view, this looks very much similar to some of the picture we saw this morning in the CAPRA presentation. And so this could be a good, could be one way I feel that could be used for also exposure at city level, but that can be extended over also large areas, and it could be even done at the countrywide. So we have tested this over a number of cities, and here is just an example of the city, and it works quite fine. I would like also to then to tell you, ask feedback from you, and simply ask to what extent can image technology help in vulnerability assessment? And vulnerability assessment in this case is defining the quality of the building. From the satellite you can tell the size, you can get the height of the building, but what else can you tell? And the interesting part is what type of building types would you like to classify? So, for example, we've seen today in CAPRA there are 5 or 6 building types that they're trying to get out. That's interesting, but there are other methods, for example, HAZUS, that have 20 building types that they would like to get out. So I think is there a consensus on what should get out? Then also, if we are sticking to our urban land use map, then also how is the different classes of the urban land use defined? And as simple as that. And then should we use also satellite imagery to identify the use of the building? We know that, for example, industrial area can be separated from residential area and so on. Is this an issue for the disaster risk community? And then should the building stock or the urban land use also used to map human exposure? So there are lots of data sets of population available at core scale. Should those, or is there an interest of the disaster risk community in downscaling those district type of information into more a fine scale information type? Well, this is the question. And what else is there needed in the disaster risk community? So this was a little bit of my overview, which I wanted just to make sure that I take from the forum to you, because I think otherwise it would not get to you. And I would like just to thank the people that have contributed not only to the forum discussion, but also providing some of the slides in this presentation, and of course all the speakers of this session. So, so this concludes my presentation. And I would like now to invite the next speaker, which is Mark Lucas. This is Mark Lucas. I would like just maybe you introduce yourself.
Okay. Might need some help with that. Hi, just a little bit background. I come from a background from the Air Force and the National Reconnaissance Office, where we did a lot of satellite image processing and advanced remote sensing. Had a opportunity to found and run a company called the Image Links, where we did commercial remote sensing for about a half a dozen years, and lately have been mainly focused on business back with the government agencies and applying open source software to the whole business of remote sensing and geospatial processing. What I'd like to do here is just sort of give a 50,000-foot overview of remote sensing, where it came from, what some of the capabilities are, and where I think it's headed, especially with regards to assessing risk and earthquake damage and so forth. One way to think of it, you can sort of decompose the capabilities into spectral, spatial, and temporal capabilities of the satellite. Spectral, we all see, or most of us see, red, green, and blue. We see the optical bands, but the satellites have the capability to see, what in the case of thematic bands, half a dozen different spectral bands, or in hyperspectral cases, 200 bands, and do very detailed characterizations of materials on the ground. Spatial, of course, is the physical resolution of what we can see in those images. Historically, Landsat gave us very broad coverage. We could do land classification. We could tell urban areas from different types of vegetation or runoff areas. And temporal is how often can we get access to that spot on the ground. Most of the satellites up there, just because of orbital mechanics, maybe every few days we can get an image of a spot on the ground. Most of the newer ones, every day we can get a spot on the ground. They're typically constrained to 11 o'clock or 1 o'clock in the middle of the day. But there's a whole range of new sensors that are coming out that are giving us almost constant vigilance of spots on the ground. There's also other factors. In the case of optical, of course, is there cloud coverage? Can we even see what's on the ground? Historically, with Landsat, spot, and so forth, there's been a lot of use for remote sensing for mining, oil, gas, for land characterization, and again, we see red, green, and blue, but up in the near infrared, there's a lot of very useful information. If we could walk outside and see near infrared, the vegetation would probably be about 10 times brighter than what you perceive optically. And stress usually shows up way ahead of time in those bands, and you can detect trends and so forth. Again, down in the hyperspectral sensors being used in oil, gas, and mining, there are scientific instruments and need a lot of calibration, but you can discriminate between types of vegetation and so forth and different types of materials. Synthetic aperture radar. The commercial world's really taken off in this regard. This is actually a picture of we're downloading virtually everything we can buy in terms of the oil slick coverage in the Gulf there, and we can get determined coverage of that because the radars, of course, don't worry about clouds, and they can you can see the black areas on there. There's also a lot of, since it is an active signal, there's all sorts of advanced capabilities like interferometry and so forth that can be applied to that, moving target indicators and so forth. We're sort of blessed. We're getting a lot of high-resolution commercial satellites up there. They're in the sub-meter range, and then on the aerial side, we're going to digital sensors. I'll show you some of that, and now on the ground basis. This is the aerial of the Haiti relief camps and the type of detail that we're getting out of that. And just to give you an idea, we're talking about with the commercial sensors here. This is just Tampa as an example, but you get a very wide area of coverage, and you can go into any spot on that at half-meter resolution typically. And you'll see, as others have pointed out, we're getting what they call a nadir view, a bird's eye view, a straight-down view of what's there. So it's good enough to basically see the outlines of buildings. We can use this on a large scale to outline those buildings, maybe roughly categorize them, but as pointed out in some of the other presentations, in cases of earthquake damage, sometimes it's hard to see if they've collapsed or not, and you really need some ground truth or oblique shots on that. LiDAR is another sensor that was mentioned. This is an active, it's basically a laser that pulses on the ground, just lots of pulses, and you get actual measurements on the elevation or the height of the features. In the case of Haiti, this is what we call a change detection product, where day by day we would run these LiDAR products. The code is red is fled, blue is new. So anything you see in blue are new refugee camps. Anything that's red are departed refugee camps from the change detection of that. And that turned out to be pretty useful. These were aerial sensors that were flown at the time. And this is just a 3D relief of the same thing over in Afghanistan, showing all the details for the structures. I think some of the more exciting sensors are the aerial digital sensors. Pictometry and others have oblique camera mounts, and they do a single swath, and you get 4 shots to the front and sides and 1 straight down, and now there's automated software to stitch it all together in automated 3D models. And there's a lot of detail you can pull out of that. You can basically go in there and determine the types of buildings from that. And I think in terms of trends, this is where the whole technology is going to take us. We're going to just get to modeling with all these automated sensors and ground-based sensors, be able to put virtual models in 3D that will help us to get a much better orientation of what's going on in the ground and attribute those with other sources of information to do better risk assessment as we go along. Trends of what we're seeing is, again, high-resolution, wide-area surveillance systems. There's all sorts of systems being put together. I've seen systems that are taking, hundreds of cell phone cameras and strapping them together and getting very wide, high-resolution systems. Of course, Predator and other drones that are given what we call persistent surveillance. They can dwell and see what's going on over a long period of time. We've already sort of covered some of the active sensors like LiDAR, synthetic aperture radar, and what's really going to happen is, and we're seeing it already, is that it's remote sensing ubiquitous. We're going to see it everywhere. In the case of Haiti, we saw what OpenStreetMap was able to do because everybody had GPS phones and could take snapshots and geocode it and easily put it into a database that's collaborative. We're all carrying around cell phones now that are sophisticated sensors in their own right with attitude positioning and better cameras built into them. Working on a lot of applications where automated tagging and sending of those images back to a central database and automatic updating of those. So I think remote sensing always has used ground truth to validate what we've seen through the sensor, whether it's been Landsat, whether it's been the aerial sensors. And what we have unfolding in front of us is this crowdsourcing of that ground truth. And we'll continue to use the thematic sensors for very wide area coverage. I think in the case of earthquakes, we're going to see a lot of the commercial sensors giving us an overall view. But really, for earthquake situations, we're going to have to get those aerial digital sensors in there, and we'll see a trend to really rely much more on the crowdsourcing and the feet on the ground and those optical sensors. And I think that they're going to be passing out. But there's we're very big on using open source software to do a lot of this. We work on a project called Awesome, which does remote sensing. It's all open source software, and those are the related links for that. Okay, thank you.
Thank you very much.